For decades, computers operated on a rigid system of rules. We called them programs. These programs were precise instructions, meticulously crafted by human minds. They excelled at tasks like arithmetic, data storage, and retrieval, but they struggled with the nuances of the real world, the ambiguity of human language, the complexity of visual recognition. These were insurmountable challenges for traditional computing. Imagine a computer trying to identify a cat in a picture. A human child could do this effortlessly. But a computer, following a set of rules, would struggle. It might look for specific shapes, colors, or patterns, but it could easily be fooled by changes in lighting, pose, or even the cat's mood. The world is full of variations, and traditional computers, bound by their rigid logic, couldn't keep up. This was the limitation of early computing. A world of information existed beyond the reach of binary code. To truly unlock the potential of artificial intelligence, we needed a new approach. We needed a system that could adapt, learn, and evolve, much like the human brain itself. This is where the story of neural networks begins. The human brain is an extraordinary organ. It is a complex network of billions of neurons interconnected by trillions of synapses. Each neuron receives signals, processes them, and transmits new signals to other neurons. This intricate dance of electrochemical activity gives rise to everything we perceive, think, and feel. Scientists and engineers, inspired by this biological marvel, began to explore a new frontier in computing. Could we create artificial systems that mimic the structure and function of the brain? This question led to the birth of neural networks. These networks, like their biological counterparts, are composed of interconnected nodes, or artificial neurons. Each connection between nodes has a weight representing the strength of the connection. These weights are adjustable, allowing the network to learn from data. Input data is fed into the network, and the signals propagate through the layers of nodes. The output of the network is compared to the desired output, and the weights are adjusted accordingly. Through this process of trial and error, the network learns to recognize patterns, make predictions, and even solve complex problems. This new paradigm in computing, inspired by the brain's architecture, promised to revolutionize artificial intelligence. It opened up a world of possibilities, allowing machines to tackle tasks that were once considered the exclusive domain of human intelligence. The journey of neural networks began in the 1950s with the invention of the perceptron. This early model, a single-layer neural network, could learn to perform simple classification tasks. It was a significant step, demonstrating the potential of artificial neurons. However, the perceptron had its limitations. It could only solve linearly separable problems, meaning it couldn't handle more complex patterns. The field faced a setback in the 1960s with the publication of a book titled Perceptrons. The authors, Marvin Minsky and Seymour Papert, mathematically proved the limitations of single-layer perceptrons. This led to a period of disillusionment and reduced funding, known as the AI winter. However, the spirit of innovation was not extinguished. Researchers continued to explore the potential of neural networks. They developed new architectures, such as multi-layer networks, and new learning algorithms, such as backpropagation. These advancements paved the way for deep learning, a powerful approach that uses networks with many layers to learn complex representations of data. Section 4. The AI Winter, a period of dormancy. The AI winter was a period of reduced funding and interest in artificial intelligence research. It followed the initial wave of optimism in the 1950s, which had promised rapid progress towards human-level AI. The limitations of early neural networks like the perceptron led to skepticism and disillusionment. The book Perceptrons by Minsky and Papert, while highlighting the limitations of a specific type of neural network, cast a shadow over the entire field. Funding agencies became hesitant to support research that seemed unlikely to deliver on its ambitious promises. The field entered a period of dormancy, with progress slowing to a crawl. Despite the challenges, a dedicated group of researchers continued to believe in the potential of neural networks. They toiled away in relative obscurity, exploring new ideas and developing new techniques. Their perseverance would eventually pay off as advancements in computing power and the availability of massive datasets breathed new life into the field. Section 5. The power of data fueling the resurgence. The resurgence of neural networks in the late 20th and early 21st centuries can be attributed in part to the exponential growth of computing power. Moore's law, the observation that the number of transistors on integrated circuits doubles approximately every 2 years, held true. This meant that computers were becoming exponentially faster and more capable. However, raw computing power alone was not enough. Neural networks, unlike traditional algorithms, are data-driven. They learn from examples. The more data they are exposed to, the better they become at recognizing patterns and making predictions. The rise of the internet and the digital age generated an unprecedented amount of data. This data, from text and images to videos and sensor readings, provided the fuel that neural networks needed to thrive. Researchers now had access to massive data sets, allowing them to train increasingly complex and powerful models. The combination of increased computing power and data availability created the perfect conditions for a renaissance in artificial intelligence.